Welcome back, everyone, to the Algebraic Graph Theory seminar. This week we have Sooyeong Kim talking about equidistant switched hypercubes.
Okay, thank you for introducing me. And then today I'm going to talk about some hypercube, and then I'm going to perform some sensitivity analysis on hypercube, and then the graph we obtained from hypercube by switching. So here, let me give you some motivation first. Here. Okay, isolating a spin network is for the construction of quantum computers. So isolating a spin network is necessary task in order to keep quantum superposition of states and coupling between qubits. So this problem brought our attention to this question. So how can a quantum spin network become insensitive to external environments, preserving perfect state transfer? So here we are going to measure being affected by external environments by perturbation in edge rate and the readout time. And then we are going to manipulate a quantum spin network in order to obtain a graph which becomes insensitive to those perturbations. So here we are going to measure manipulation as switching edges. So this is our objective by hypercube, which is the graph whose vertex set is the set of binary strings, and their adjacency is given by two binary strings differ at exactly one coordinate. And then here we use the following the definition for PST here. A of G is given by the adjacency matrix of the graph, weighted graph. And then here we are going to consider U of T, which corresponds to continuous quantum walk, and e to the power of ITA. And then the fidelity of state transfer from V to W at time t is given by the square of modulus of entry in the matrix U of T labeled by V and W. Especially we are interested in this measure, this quantity. When P of T naught is 1, we say that there is perfect state transfer. We are going to use abbreviation to say PST from now on between two vertices. So the following proposition is a well-known fact. Given a hypercube, and then when we pick any vertex, then that hypercube exhibits PST between two vertices, X and X star at time pi over 2. Here, X star is the antipodal vertex of X, because in hypercube, for each vertex, it has unique antipodal vertex. That's why I'm going to use this notation X star as its antipodal vertex. And then here, let me talk about the ultimate goal of this work. Here, our goal is to obtain an insensitive graph to the change of the readout time or the weight of edge rate. So here we have a Qn, and then S is any vertex, and then S star is its antipodal vertex. And then here we are going to obtain Q tilde n by switching these two edges. Here the thing is we want to compare two graphs, similar with similar properties. So we do not want to compare apple and orange. We want to compare some oranges from, let's say, California and Florida, right? So Qn here, it exhibits PST between S and S star, and then Q tilde n, well, our desired property is to have PST between S and S star in Q tilde n too. So that's why I intentionally switch these two edges. When you observe these two edges, then this is the matching, which is the set of edges whose two edges, any pair of two edges are incident. So not incident, sorry about that. So here, and then furthermore, for these two vertices, they are at the same distance from S. And then here, these two vertices are the same distance from S. The reason is here, when it comes to the distant partition with respect to S in Qn, for example, then that distance partition is the partition of vertex set according to the distance from S. For example, here, we are going to choose this single vertex, and then we are going to collect these vertices, whose distance from S is 1. And then we are collect those vertices, and then we are going to collect another vertices whose distance from S is also distance is 2. So this partition is called distance partition with respect to S. And then for that, for this resulting graph, when we think about the distance partition with respect to S, that's the same as that of Qn. So this property enables us to obtain PST between S and S star in the resulting graph. So in this case, we are going to compare the sensitivity. Of course, we have to make sure that they are non-isomorphic too. So we are gonna, I'm going to show that later. So here, now we are gonna perform the sensitivity analysis on these two graphs with respect to the readout time and the edge weight on a particular edge, especially S and K here. So as a result, about the readout time, they have the same sensitivity. And then this is proved. And then regarding the edge weight, they have, it's not proved yet. So based on the experiment, they have different sensitivities, especially Q tilde N becomes insensitive to the change of edge weight, especially S and K. So you might be wondering about what if we perturb the other edges, for example, here or here, something else. So for my impression, based on the experiment, when we perturb some edges here, for example, here, away from this matching, then the sensitivity will become increase. I mean, Q tilde N becomes sensitive when you perturb some other edges. So it looks like equilibrium. So here, when you perturb this part, then Q tilde N becomes insensitive, but the other part, when you perturb the other, then Q tilde N becomes sensitive. So this is our observation, and then we want to prove insensitivity of Q tilde N about this particular edges. So here, let's consider this graph. Q1 and Q2 both their function of the fidelity of state transfer from S to S star at time pi over 2, especially we consider some particular hypercube, Q6 and Q tilde 6. Then, as you see here, x-axis is about the edge weight. So when edge weight is 0, of course, they obtain PST here. And then when we perturb edge weight, then their fidelity is going to be less than 1. And then here, in order to show that the resulting graph becomes insensitive, then we need to show that Q2, which corresponds to Q tilde 6, is above the graph of Q1. In other words, the second derivative of the fidelity with respect to the edge weight for Q6, Q tilde 6 is greater than that of Q6. Because when you think about it's decreasing, then we have to show that the second derivative is greater than this. So to reinforce the observation, because it looks very similar, so we consider the difference between Q2 and Q1. We have this result, which means Q2 is above Q1. So this is our ultimate goal for this work, proving that Q tilde n is more insensitive than Q tilde Qn with respect to the perturbation of edge rate. Okay, so what we are gonna do is now, so we are going to sort of generalize this matching, and then we are gonna explore some, and then we are gonna define switching based on, we are gonna define switching based on this matching. So this is our first job. Okay, given a graph G, and then we are going to pick a matching of size K here, V1, W1, and then V2, W2 up to VK, WK. Those edges comprise a matching in G, and then we are gonna impose more condition on those matching, that matching. Then here, oh, this is typo, sorry about this. So here, distance between V1 and V2 should be A, not 2A. So yeah, this should be A. And then here, mutual distance between VIs in those vertices is constant as A. And then similarly, mutual distance between WIs for those vertices is constant as B. So if that matching satisfies these conditions, then we call it equidistant matching. Here, this is the formal definition. So when we pick a matching in a graph, then it's said to be equidistant if there exist two subsets such that mutual distance between VIs in this set is constant. And then similarly, mutual distance between WIs for this set is also constant. And then we also use this terminology for these two subsets. For these two subsets, we call them distance partite sets. Okay, and then sometimes we want to specify some parameters. When we consider equidistant matching, then we want to specify the number of edges in the matching. And then what about the distance for distance partite sets? So we use the following parameters, K, A, B, gamma in this way. So K means the number of edges in the matching, and then A is the distance, mutual distance between VIs, and then B is the distance between WIs. So in this way, gamma is about the multiset of distances between VI and WJ, where I and J is in here, and then I and J are different. So by using this definition, by using equidistant matching, we are going to define equidistant switch in this way. So given an equidistant matching in this way, and then we are going to delete those edges. Oh, sorry, I should have mentioned this first. Before we switch those edges, we are going to consider the ordering of these edges. So which means we are going to permute these edges. So here, tau, which is permutation in the symmetric group, this represents the permutation of those edges. I mean, we are gonna reordering of these edges, and then we are gonna switch them. So in this way, delete these edges, and then we are gonna add edges in this way. So here's the formal definition for an equidistant switch. So here, given M, which is equidistant matching in a graph with distance partite sets as follows. And then we are going to pick tau in the symmetric group. And then here, M sub tau denotes the set of ordered edges. So according to the permutation tau. And then we are going to delete those edges, according VI and WI. And then we are going to add edges in this way, as seen in the picture in the previous slide. Then this process is referred to as the equidistant switch via M sub tau. And then if we want to specify some parameters regarding equidistant matching, then we consider K, A, B, gamma switch. We also use this terminology. Let me show you an example in the next slide. Sorry about many definitions here. And then the graph obtained from G by the equidistant switch via m tau, we are going to use this notation. And then we call the graph as the equidistant switched graph via m tau. Here, let me show you some example here. So let's consider graph G. And then as you see here, these 4 edges comprises equidistant matching. Here, 4 is the number of edges in the matching, and then 2 is the distance between here V1 and V2 and V1 up to V3, etc. And then those mutual distances 2. Similarly, we can see that the mutual distance is 2. And then here 3, you can see V1, the distance between V1 and W2, it's 3. And then V1 and W3, it's also 3. And then similarly, you can consider the other distances, and then we can check it's 3. And then here, we are gonna pick the identity permutation. Then M sub, then, sorry about that, okay. And then we also consider another permutation, tau 1 and 2, which is in cyclic notation. Then let's consider this graph, G tilde super M sub ID, which means we are going to permute those 4 edges according to this identity permutation. Then here V1, W1, and then like this. And then if we permute those edges according to tau, then we have this picture. Of course, they are the same. And then we are gonna apply the switching here. So delete those 4 edges, and then we are going to add edges V1, W2, V2, W3, and then V3, W4, and then V4 and W1. And then here, we are gonna delete those 4 edges, and then V2, W1, and V1, W3, and then V3, W4, and then V4 and W2. So in this way, the resulting graphs are respectively in this way, G tilde super M sub I, and then G tilde super M sub tau. And then you can we can verify this. They are not isomorphic because one can check this observation. So they are not isomorphic. What I want to say is according to the choice of permutation in the symmetric group, we have different non-isomorphic graphs. So that's why here we are going to use this notation. So since they are not in general isomorphic according to the permutation, so here we are going to consider this. G tilde M sub tau is isomorphic to G tilde M sub sigma for all sigma in the symmetric group. Then yeah, we use this notation just without using the subscript. So we use this notation from now on if we have such a thing. So basic observation is, for example, if we have 2 edges in an equidistant matching, then we only have one option. So suppose that in this graph, we only have 2 edges in equidistant matching, then we only have one option to switch those edges. So in this case, for example, in this case, Q4, which is hypercube of order 4, and then let's consider these 2 edges. Then this is an equidistant matching with this parameter, because there are two edges, and then distance is as follows. So the symmetric group is just identity permutation, and then this. So we only have one switching, one possible switching. So yeah, we don't need to consider about permutation here. And then once we switch those two edges, we have the following graph. And then here, okay, so here we are going to use this notation because those two graphs are isomorphic. So we are going to use this notation without subscript. And then, oh, I should have written here 4. And then here we can verify that this graph and then previous graph, which is hypercube of order 4, they are not isomorphic by checking this. For example, here, for this vertex, in the hypercube, this vertex and this vertex, they are antipodal vertices. But for this graph, they lose that property. So because the distance is 1 and 2. So yeah, this tells us that they are non-isomorphic. Of course, we are gonna provide a formal proof later. And then here, let's think about another stuff. So let's pick these two edges, for example, here 0, 0, 1, 0, and then 0, 1, 1, 0, and then this edge. And then these two edges comprise an equidistant matching, right? Because that's a matching, and then mutual distance is 2 and 2. So what I want to say is here we switch these two edges, and then for this time we are going to switch these two edges. Then how can you say the resulting graphs are isomorphic or not? Because if two resulting graphs by switching these two edges and these two edges, they are non-isomorphic, then we have to consider two graphs when you think about equidistant matching with this parameter. So what I want to say is if that matching is transitive, so in other words, if we can find an automorphism that maps these two edges to these two edges, then we may just analyze this matching, this one type of matching, right? If there's no automorphism between these two matchings, then we have to analyze two types of graphs. So that's why we are going to consider transitivity for this matching. Then here, if that matching is transitive to another equidistant matching, then we may use that article the here instead of a, because we can identify all the this type of matching with one particular matching. So that's why we can use the article the here. So here, this proposition is about the transitivity of equidistant matching, especially these parameters. And then about the other parameters, yes, there's some counterexample can be found. So here, let me state this proposition. So given n, which is greater than or equal to 3, and then given an equidistant matching m and n with these parameters, then there exists an automorphism f such that this matching can be mapped to this matching. So in general, for this type of equidistant matching, we may use the these parameters switched n cube. In other words, given an n cube, and then if you pick a particular equidistant matching with this parameter, and then once you perform switching there, and then you may say that resulting graph as the this parameter switched n cube. This allows us to analyze one specific graph instead of considering all the others switching. So, okay, and then let's consider this theorem. which is about the non-isomorphism between Qn and the resulting graph, which is obtained by switching. So here it's a bit more general version, because we do not consider equidistant matching. So here, given Qn, and then let's pick any matching in Qn, then we are gonna apply the process of switching that we have seen as the switching, equidistant switching. Then when we apply the switching like this, then the resulting graph H is not isomorphic to Qn. So the proof is done by considering the second condition here. So this is the equivalent. This is a equivalent condition for G to be N-cube. So we have three conditions, and then especially we focused on second condition, and then we use the contradiction. So we are able to prove this. So this implies that hypercube and equidistant switched hypercube are not isomorphic. Okay, and then let's consider about PST for the equidistant switched graph. So here, M, given M as an equidistant matching in a hypercube, and then we are gonna pick vertex in a hypercube such that X is the same distance from V1 up to Vk, and then these vertices comprise one distance partite set, and then X is also is the same distance from W1 up to Wk. So in this case, for any permutation tau, an equidistant switched graph, X and X star pair up to exhibit PST at time pi/2. So let's consider this example again. In this case, 0, 0, 0 is the same distance from 1, 0, 0, 0, and then 0, 1, 0, 0. And then this vertex is also the same distance from here, 1, 0, 1, 0, and then 0, 1, 1, 0. And then we switched those two edges. And then this is the resulting graph. And then the theorem says that this graph exhibits PST between these two vertices, 0, 0, 0, and 1, 1, 1, 1. And then here, there's a conjecture for this theorem, for the proof of the converse of this theorem. So for this theorem, actually, for the proof of this theorem, we considered equitable partition. So I have told about the distance partition with respect to X in Qn and Q tilde n before, because since they have the same distance partitions, so we have the same equitable partition, so that we have the same symmetrized quotient matrices. So this implies that X and X star pair up to exhibit PST. And then for the proof of the converse is it doesn't look easy. And then here, since we haven't proved conjecture, so we have the following proposition. So especially M is given by an equidistant matching with this parameter, then we have the least number of vertices to pair up to have PST in this graph. So for example, when we plug NS4 and then alpha is 1, for example, then this number is 8. So it says that at least 8 vertices pair up to have PST. So let's go back to this example then. Here, this is N is 4, and then alpha is 1. And then the proposition says that 8 vertices pair up to exhibit PST. Then one can verify that excluding 8 vertices here. So for example, this vertex, which is involved with switching, then this vertex has its antipodal vertex in Q4, which is 0, 1, 1, 1. Then this pair is going to be excluded for exhibiting PST. And then for this vertex, similarly, considering the antipodal vertex in Q4, which is this vertex. So those pair does not exhibit PST anymore in this resulting graph. So excluding 8 vertices, we have 8 vertices to pair up to have PST. So, and then here we still have to put at least here because this conjecture is not proved yet. And then one might be wondering about this counting vertices pair up to have PST. Then here, for example, when we change this number as 3, then our matching has 3 edges, and then one might be interested in finding the number of vertices, but it seems tricky. I mean, yes, it was not that trivial. So yeah, that could be an interesting question anyway. And then, okay, now we have hypercube and then equidistant to switch the hypercube. And then they are not isomorphic. And then they have PST between some pair of vertices. And then we want to compare the sensitivity between those two graphs with respect to readout time and the edge weight. So this theorem here is about the sensitivity with respect to readout time. And then it says that hypercube and the equidistant switched hypercube both have the same derivatives of the fidelity with respect to readout time, which means they have the same sensitivities. And then for the proof of this, we have to prove this proposition. And then the implication between these two statements is from this paper. So in other words, the derivative of the fidelity with respect to readout time can be written as some combinatorial expression. So this proposition is about, given an equidistant matching in hypercube, say M, and then we are gonna pick a vertex X and then any permutation tau. And then X is the same distance from the vertices V1 up to Vk, and then W1 up to Wk. And then the number of walks of length J from X to itself is the same as that in the resulting graph. So this proof is done by finding bijection map between two combinatorial sets here. And then here, yes, constructing, starting from this walk, and then we construct the walk in this graph. So, and then we also prove that that the algorithm, the construction is reversible. So that makes us to have bijection map between two combinatorial sets. That's why we have this proposition, and then that implies this theorem. So, and then now we are going to focus on the sensitivity with respect to edge weight. Okay, here, let me start with some notation here. Given a graph, a weighted graph G, and then G exhibits PST between two vertices S and R at particular time T naught, then the derivative of the fidelity of state transfer between K and L with respect to the weight between, PST between S and R, with respect to the weight between versus K and L, then that derivative is denoted as this. And then similarly, we use the following, this notation to denote the second derivative of the fidelity with respect to the edge weight. Then one can, we can easily find that the first derivative is 0, and then second derivative of the fidelity with respect to the edge weight is less than or equal to 0. So we only have to consider second derivative. Then here, let me remind you of our particular edge, which is here. So there's a equidistant matching, and then we switch them. And then here we focus on this edge, which is involved with equidistant switching here, and then this is adjacent to the vertex, which exhibits PST. And then the reason is this is the most simple case. I mean, this is simplest case. That's why we consider this. And then we can consider other cases. For example, the matching, which is distance from S as 2, for example, like that. And then because we will see that computation is going to be heavy. That's why we are focusing on the simplest case. Here, to find the second derivative for the, with respect to edge rate, we need to think about perturbation theory here. So given a weighted graph G, and then here, since we are going to perturb particular edge, K and L, that's why we consider this matrix E, which is rank is 2. And then here, A plus H E, which is perturbed matrix, can be diagonalized in this way. And then V of H is orthogonal, and then lambda of H is diagonal matrix. And then we use this notation, round V over round K and L, and round lambda over round K and L to denote these matrices. I mean, the matrix obtained by differentiating with respect to H and evaluating at H is 0. And then similarly, yeah, we can also find this matrix. So for simplicity, we use this notation V and lambda as V of 0 and lambda of 0. And then here, considering this U of T, and then think about the fidelity between S and R. And then when for some T naught, there's a PST between S and R. And then the entry U of T naught, which is labeled by S and R, can be written as alpha plus I beta. So in this case, we can find the formula can be found in this paper. So let me get to the point here. So to find this, T naught is given. We need to find Y1 and Y2. And then Y1 and Y2 look like this. Then, so this V consists of, because we plugged H as 0 here. So V corresponds to, consists of eigenvectors of the adjacency matrix. But this V is not just any eigenvectors. So this V can be constructed by some algorithm in this paper. And then we are not going through that algorithm in this work, in this talk. So we just suppose that we obtained this V, this particular V. And then based on this matrix V, we can obtain the other stuff. So let me show you that in next slide. Okay, here our objective is hypercube. So let me define A sub n as the adjacency matrix. And then it is well known that the eigenvalues of this matrix are given by n minus 2j, and then each multiplicity is given by n choose j. And then we are focusing on particular edge, say K and L. Then the matrix B, as seen above, this is an orthogonal matrix. And then suppose that we obtain that matrix according to the algorithm 3. The algorithm in this paper. Then AN can be written as V lambda V transpose. And here by using this V, round lambda over round K and L can be obtained by that. And then we are going to pick eigenvectors in the matrix V that corresponds to eigenvalue n minus 2j. Then round V over round K and L can be obtained in this way. So here, R is defined as this. And then according to the rank of R, we have two types of computations for round V over round K and L. And then in case of rank is 1, then we have the following. So here, you could be wondering about what is X1? I mean, what is the criterion of choosing X1 here? X1 is the vector that comprise of a basis of the column space of R. So here, X1 is chosen according to the algorithm stated in this paper. So let me skip this part actually. So once we choose some basis of this column space, then for that, the index corresponding to this vector, we have to compute this part. And then we can see that we have to compute this, the matrix. I mean, here the dagger means the Moore-Penrose inverse. So we have to compute the Moore-Penrose inverse of this matrix. And then this matrix is symmetric, and then that inverse can be concretely obtained actually. And then another case is rank of R is 2, then we have the following formula, and then it's a bit more complicated in this case. Especially, I want to make a note here about this. So especially for this part, the numerator for this expression, if we are considering a hypercube, then this numerator is 0. But if we are going to consider equidistant switched graph, a hypercube, then this numerator is not going to be 0. So that fact makes us some difficulty of proving the conjecture actually. Okay, here based on the formula about the second derivative, and then here from this observation, we can find the second derivative for hypercube. So here, Hn is the standard Hadamard matrix, which is inductively constructed here. And then one can verify that Hadamard matrix consists of the eigenvectors of the adjacency matrix of hypercube. And then the thing is, the matrix consists of 1 and -1. I mean, every entry is either 1 or -1. So examining sign pattern of the matrix, Hadamard matrix, we can find the matrix V, and then from that matrix V, we can obtain round V over round KNL. So computing those things and then applying the formula, we have the following theorem, which is the second derivative of the fidelity between S and S star at time pi over 2 with respect to the edge weight. And then as you see here, each expression has negative sign. So which means this second derivative is negative anyway. And then what we have left is now to compute the second derivative of the fidelity with respect to the edge weight for Q tilde n. So that thing is way more tricky. And then I'm going to show you the sorry.
Yeah, copy hook it up.
Oh.
Sorry, Sooyeong, I just accidentally muted you. So if you could unmute yourself.
So how many minutes do I have left?
Another 5-ish.
Oh, okay, I see. Okay, so the point is, let me wrap things up right now then. Here, the point is to compute the second derivative, then we need to understand first the spectral property of the adjacency matrix of the graph. And then according to the algorithm in this paper, we have to construct the matrix V. And then we have to apply these equations, these formulas for round V over round KNL. And then we have to find second derivative. So the thing is, here we completely determine the spectral property of the equidistant switched hypercube for the particular switching here, this type of switching. So constructing a hypercube in this way according to particular ordering of the binary strings, and then we can apply here equidistant switching here, And then we apply some equitable partition. And then we apply some equation here. As you see here, C is 1 and -1, which cannot be obtained by equitable partition. So we have to apply some other method here. This is just by observation. So by using those things, and then we are able to obtain the spectral property of the equidistant switched hypercube, especially for this type of matching. And then, yeah, this theorem provides multiplicity and then eigenvalues, and here particular orthogonal matrix that diagonalizes this adjacency matrix. So by using those information, we can construct Vn round V over round K and L. So those things are provided in my dissertation, but there's some difficulty of combining all the information to obtain the second derivative because of heavy computation. And then we also have to compare the second derivative as stated in this conjecture here. So we found this second derivative, but for this case, it's not pretty. I mean, the expression is not that pretty. So there's some difficulty for comparing those two quantities. And then, yes, that's it for my talk. And then thanks for paying attention to my talk.